Hello viewer, welcome back to a series of liquid state. In our previous session, we have discussed on attraction, intermolecular forces, dipole-dipole interaction, London forces, etc. In today's session, we are going to discuss caloric equation of state for a liquid. We are going to discuss structure of liquid, radial distribution function, models of liquids, structural differences between solid, liquid and gases. Now come to first liquid state. A liquid like a gas has no definite shape and always take up the shape of the vessel wherein it is placed. However, it has a surface limiting the space occupied and hence a definite volume. The molecules in a liquid have strong cohesive forces like solid, but the molecules are not rigidly fixed as in solid. Liquid is much less compressible and far denser than a gas. The densities of liquids and crystalline phases of the same substance are usually only slightly different. Thus, the liquid state is an intermediate between gaseous and solid state. This, however, does not mean the properties of a liquid lie midway between that of the solid and gas. The most of the cases, it is found that liquid has some solid-like and some gas-like properties. The liquids are characterized by strong cohesion. The forces or interaction which bind the molecules together are called intermolecular or van der Waals forces, which we have discussed in detail in our previous session. An equation connecting the total molar energy of a fluid, may be gas or liquid, with its volume and temperature is called caloric equation of state. If capital E is the total molar energy, that is energy per mole, then E is equal to E kinetic plus E potential together makes the total energy of total molar energy. In an ideal gas, the molar energy is entirely kinetic in nature and depends only on the temperature of gas. Hence, E is equal to E kinetics. In the gas, there is no potential energy. All the molecules are moving. So, there is a kinetic energy. E is equal to E kinetic, but E kinetic is equal to 3 by 2 RT. Thus, E is equal to 3 by 2 RT. This is the caloric equation of state for an ideal gas. In a liquid, intermolecular forces exist which gives rise to potential energy. Here, the potential energy comes into account. This depends on intermolecular distance. Thus, the potential energy of a liquid depends on volume and it is given by minus A upon capital V, where small a is a constant which depend upon the intermolecular attraction and V is the volume. Hence, the total molar energy is equal to E is equal to E kinetics plus E potential, that is equal to 3 by 2 RT minus A upon capital V. This equation is known as caloric equation of state for a liquid. The molecule in a liquid are in contact with their neighbors, but they can move past and tumble over one another. When we imagine a liquid, we can think of a jostling crowd of molecules. Jostling crowd, the molecules which are coming together and pushing one another, each one constantly changing places with its neighbor. A liquid at rest is like a crowd of people milling about in a stadium. A flowing liquid is like a crowd of people leaving a stadium. The liquid's phase of matter is the most difficult to visualize. We have seen that a gas phase molecule moves with almost complete freedom, whereas a liquid molecules cannot move easily or freely. The intermolecular forces from other molecules are minimal and movement is highly disordered. In the solid phase, a molecule is locked in place by intermolecular forces and can only oscillate around an average location. The liquid phase lie between the extremes of gas and solid. The molecules are mobile in liquids, but they cannot escape from one another completely. Observe compactness and cohesion in liquid indicate their structure to be similar to solid, while the comparative ease with which the liquid flow and diffuse indicates a disordered random structure like in the gas. So, the liquid is in between the gas and solid. Here the structure of liquid, look how the liquid molecules are moving, but they are not completely separate. And next picture we will discuss later on. X-ray examination of many liquids reveals a certain degree of the order in the arrangement of molecules, though to a lesser degree as compared to the solid. The structure of a liquid may be described in terms of radial distribution function RDF, by means of which the X-ray diffraction data on liquid are usually interpreted graphically. For calculating RDF, a series of concentric spheres are drawn around the reference molecules in such a way that the volume interval between two neighboring spheres is constant. RDF, that is radial distribution function, then is average number of molecules contained between each spherical shell, and thus is the measure of average particle density as a function of distance from an arbitrary origin. It is calculated to be 4 pi r square d, where d is the average density of liquid in atoms or molecules per cc. If all the intermolecular distances were equally probable, that is, if the liquid were completely devoid, the holes were gone, of regularity of structure, there would be a continuous scattering of X-rays and hence no diffraction maxima or minima, but a few maxima and minima observed in actual experiments in liquids indicates the existence of regular pattern or order in them, as just like in solid, regular pattern of molecules. The maxima and minima in the distribution curve of liquid indicates the intermediate position of liquid state. Very small number of these maxima and minima suggest the existence of short range order only. In case of solid, this range is very high, but in liquid this range is very short. The regularity of order structure in liquid is lost beyond 10 angstrom. Thus, a liquid may be considered to have crystal like structure, except that the well ordered pattern extends over a short range instead of over the entire mass. There are following 4 approaches to be liquid state, that is, we are going to discuss about the model of liquids. First, cybotatic group model, second kinetic molecular models, third one liquid as a modified solid, and 4 random packing model. First, cybotatic group model. According to this model of liquid suggested by Stewart, a large number of well ordered groups called cybotatic group, each containing a few hundred molecules, are embedded in a mass of disordered molecules. These groups are not, however, permanent, and there is a dynamic equilibrium between cybotatic groups and disordered molecules. Is it clear from this? Cybotatic group is dynamic equilibrium with disordered molecules. Second model, we have second model, liquid as a modified gas. According to this model, the liquid resemble gases in all aspects except closely packed molecules with appreciable attraction among them. About the critical point, there is no distinction between liquid and gaseous state of a substance, and the so called fluid state exists. So, the liquid may be treated as a modified gas. Another model, we have liquid as a modified solid. In solid, there is a well ordered arrangement of molecules throughout the whole mass, and each molecule is surrounded by a set of other molecules in a particular symmetrical pattern. On melting the solid, when we melt the solid, expand only 10% in volume or 3% in intermolecular spacing. Therefore, it is reasonable to conclude that in liquid state a molecule must still remain in the vicinity of some other molecules surrounding it. The ordered arrangement is not therefore completely destroyed when the solid changes into a liquid. Thus, a liquid may be regarded as a modified solid. Fourth model, that is random packing model. This model was developed by Bernal and Scott, and according to this, the liquid state is a random pack of molecules. That is, the liquid structure is disordered but relatively close packed. A pentagonal structure of liquid is assumed to introduce a small disorder factor instead of hexagonal structure as in the solid. That is, only 5 surrounding atoms to an atom are permitted. The packing in liquid state is close but still loose because there is a pentagonal structure. Now, we are going to discuss about the structure differences between solid, liquid and gas. What is difference between a solid and liquid and gas? Structure of solid, liquid and gases can be described on the basis of kinetic molecular theory. Molecules first of all come into the gas. Molecules in a gas are in a state of constant random motion. Molecules of gas are moving here and there. The space between the molecules is large and therefore, there is a negligible force of attraction between the molecules. Hence, here the attraction between the molecules of gases are negligible. In liquid, the molecules are in contact with each other. The forces of attraction between the molecules are strong enough to hold them together. All the same, the molecules are able to move past one another through available intermolecular spaces. The molecules in liquid move in a random fashion. At any instant, the molecules may form cluster, leaving vacant space or holes here and there. In solids, there are strong intermolecular forces, thus fixing the position of each molecules. When we have the strong intermolecular forces, the molecules are very closely packed and fixed together. The molecules in a solid are not able to leave their position, whereas in liquid and gas they can move here and there. However, a small oscillation or vibration around mean position is possible in solid. In solid, molecules, atom or ions are tied and arranged in regular pattern due to very strong cohesive forces and are not free to move about, that is, have no translation or rotational degree of freedom. They cannot translate or transform or rotate. In gas, the molecules are in chaotic motion and there is no regular pattern in the arrangement of molecule. The liquid are intermediate between solid and gases, although a regular pattern or order exists in liquid, but the order pattern is limited to a short range instead of over an entire mass. The regularity of order structure in liquid is lost beyond 10 angstrom. Due to thermal motion, this order structure is changing continuously in liquid. So, in liquid, the structure of molecules is ordered only for 10 angstrom. After that, it can change. Here the structure, this picture clearly differentiate between solid, liquid and gas. In solid, look the solid structure, the molecules are orderly spaced, they are well ordered, there is no intermolecular space in between the molecules, the attraction forces between the molecules of solid are very strong. So, they are in a solid form. Now, come to the liquid, here the molecules are scattered, the intermolecular space between them is high than that of solid and there are many holes are presented in the liquids. The molecules can move here and there, they can, but they cannot escape each other. they can move, they can change their place here to there. Now, the third picture is showing the gas. In this picture, molecules of gas are moving here and there, can move easily. They have more intermolecular space in between. There are minimum intermolecular forces in between them. So, they can move here and there and can move freely. So, this picture clearly indicates the differences between liquid, solid and gas. Here is another picture which can easily differentiate all the three terms, that is liquid, solid and gas. Here the picture is solid. Look at this picture. The solid are only vibrate, they can oscillate, they cannot move, only vibrate. Look second, that second picture is of liquid. Here liquid molecules are moving, they move here and there, they can change their position, they can move up and down, but they cannot move freely. But in third picture, look, this is the gaseous stage. In gaseous, the molecules are freely move, and fourth one is another state, that is called plasma. How can we come into the plasma state? Here a solid, when a solid heated or a solid is given to a temperature, it take heat and it converted to liquid. When we give temperature to liquid, it converted to gas. And then if we give temperature or we heat a gas, then it come to plasma, that is fourth stage. Fourth state, that is plasma. Plasma, in plasma the molecules of gas are heated, they are charged particles. Here what is solid, what is liquid and what is gas and what is plasma. Here solid, tightly packed in a regular pattern, vibrate but do not move from place to place. If we give heat, it converted into liquid. In liquid, what is liquid? Close together with no regular arrangement, vibrate, move about and slide past and each other, that is liquid. If we give the heat to liquid, it converted into gas. In gas, the particles well separated with no regular arrangement, vibrate and move freely at high speed in gas. If we give the energy to gas or we give temperature to gas, it converted into plasma. In plasma, what is plasma? In plasma, molecules has no definite volume or shape and is composed of electric charged particles. So, it is all about the structural differences between solid, liquid and gases. Now, we are come to the conclusion of this session. In this session, we have discussed caloric equation of state for a liquid, structure of liquids, RDF, that is radial distribution function, different models of liquid, and lastly we have discussed structural differences between solid, liquid and gases. In our next session, we will discuss